is f of m plus n, okay? So if you have an n plus n here, you'll have an n plus n here. I mean, pretty trivial, okay? I'll just assume this mapping is homomorphic, and it's just a one-line proof. I assume you can do that as yourselves as homework or whatever. All right. Okay. So f is homomorphic. So let's find its kernel, right? So that's the subset of these integers that I to the n are equal to 1. Well, what are these values of little n? What integers are such that I to that power integer is 1? Well, 0, plus minus 4, plus minus 8, plus minus 12, plus minus 16, dot, 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 right? In other words, 4z. Z is the set of all integers, and 4z is just multiples of 4. What I just said, 0, plus minus 4, plus minus 8, okay? So that's your kernel, right? It's the set of integers where this property is satisfied. So your kernel is just 4z, right? So the quotient group, now we've got the kernel, we know the kernel is a normal subgroup, right? So we can create a quotient group, and here it is. Here's our original group G, right? The set of integers, and here's our normal subgroup. It's 4z, and that normal subgroup here is the kernel, right? That's the kernel. So this quotient group here is the quotient group of the kernel here, right? And it will have four elements. And these elements are cosets, right? That's what a quotient group is. It's a set of cosets. It's a group of cosets, and the binary operation for those cosets. And you take any two cosets, and you perform a binary operation on them, which is what I've been calling subset multiplication, where you take any two elements and you binary operate on them using the binary operator, the little circle of your big group G, your starting group. Right? Well, here are those four cosets. Right? There's just 4z, that's your unit of your quotient group. Right? That's your, that is the kernel. And then 1 plus 4z, and 2 plus 4z, 3 plus 4z. That's as far as you can go. God, it's still there. Now, if you had 4 plus 4z, that would be absorbed into 4z. Right? So that's it. You have 4 cosets. So your quotient group consists of 4 members, four cosets. And I suppose I could. I should say maybe what. I mean, this is not in the textbook, but usually you're asked when you're talking about the quotient group. You're usually asked to say. What other group is it isomorphic to? Well, can you see if you take this element here? Can you see that that's a generator? Like if you take the if you binary operate in this coset with itself, then you'll get 2. And if you binary operate that with that, well, if you do this 3 times, you get 3. And if you do it 4 times, you'll get this. So you've generated all 4 cosets using this. So this is the generator, okay? And if a group has a generator, it means it's cyclic. So this is a cyclic group of order 4, okay? So this quotient group here is isomorphic to C 4, the cyclic group of order 4, right? What I've just said, it's not in the text. I'm just adding that because it's done elsewhere, but Barnard didn't talk about it here. All right, second example. You've seen this before as well. Now we're talking about direct products, right? Direct product in the context of groups called direct product. In the context of sets, it's called Cartesian. Is that right? Cartesian product. So it's a way of the direct product is a way of generating a larger group from two smaller groups. If the group, or if your group G1 is of order M, and the order of your second group G2 is N, then the order of your product group G1 times an X, big X, G2 has an order size of M times N, right? Okay, so we're mapping here a product group to another product group, but of smaller size. The order of this product group is 4 times 4, so that's 16, right? And the order of this target group is 2 by 2, so that's 4. So we're mapping a group of 16 elements, 4 by 4, to TO, a smaller group of order 4. So it's a many-to-one mapping. And that's pretty typical of homomorphic functions. Isomorphic functions map 1-to-1, right? There's a bijection between the elements. The target group, the starting group and the target group have the same number of elements when you're talking about an isomorphism. But here we're talking about a homomorphism, and we're mapping 16 elements to 4. So it'll be like a 4-to-1 mapping. Right? Now that's the mapping between the starting group and the target group, like between sets, if you like. And here's the mapping between an element and another element. So we're mapping this element of a product group, right? So now, what are these? These are residue classes, right? Residue classes. So we have a direct product of 2 residue classes. Don't forget the comma here. Right? That's, remember the definition of a direct product. If you're rusty, go back quite a few lectures now and revise the definition of a direct product. Right? So here you're mapping this element into this element. Now we've handled this a bit before. We've shown that this mapping function f is homomorphic, right? And we also found the kernel before. So this is now a revision. I won't go through the theory. So go back to earlier lecture or 2 or 3. The kernel for this mapping was well, I'll just say it in shorthand. So it's naught mod 4, so residue class, remember? So, well, 0 mod 4, comma 0, 4. And then I'll shorten it even more. So 2, comma 0, 0, comma 2, and 2, comma 2. So I've used it like a double shorthand. Because really, strictly you're talking residue classes and you need to know what the modulus is. Yeah. Alright? Okay, so this starting group has order 16, right? Has 16 elements. The kernel, we have 1, 2, 3, 4 elements. Okay, so the size or the order of the kernel is a normal subgroup. Has order 4. So what is the order or the size of the quotient group? Well, you remember the formula? You take the the starting group size, which is 16, this one, again, and divide it by the size of your normal subgroup, so the size of k, which is 4. So the size, that's what these vertical bars mean, right? So the size, the order of the quotient group, the whole thing here, will be 16 divided by 4, which is 4. Now remember, quotient group is just a set of cosets, so we will have 4 cosets in this quotient group. It will consist of 4 cosets. The kernel, right, and these. Now you notice it's 1 or 0, 0, 1, 1, 1, and k is, well, you could have 0, 0 here. It doesn't change anything. Now, notice there's no 2 or 3 here. Why? Because of this, right? These are. Why is that? Because the target group has mod 2s. So if you have 2 or 3, the mod 2 will change it to 0 or 1. Okay, now these 1, 2, 3, 4 cosets, they're distinct. We can prove that by contradiction. So the usual proof by contradiction. You assume something to be true that really you think it's false, but you're trying to prove that it's false. So you assume it's true, you derive contradiction, and therefore what you assumed was true must be false. Right? So let's prove this. Let's prove that these 4 cosets are distinct. They're different by assuming that 2 of them are the same. Okay? And then we'll get a contradiction, and therefore those 2 cannot be the same. Right? So let's take any 2. In general form, I don't know, we can take this one and say that one, whatever. So in general form, you'll have I mod 4. Now remember, these are residue classes. I mod 4 j of 4 plus k is equal. That's using proof by contradiction now. K mod 4 L mod 4 plus k. Right? Where these I, j, k, l, all of them have value either 0 or 1. Okay, so I, j, k, l belong to either 0 or have value 0 or 1. Okay, now if this coset equals this coset, right? We've done this kind of thing before. Go back to, I think, coset, to the chapter, the lecture on cosets, which was, just a minute, what lecture number was that? Cosets.